So in a previous video, we were talking about sample variances, and we alluded to working with chi-square distributions. So to refresh your memory, we said that if our random sample comes from a normal distribution, then the random variable W being n minus 1 times the sample variance random variable divided by the population variance has a chi-square distribution, which is like a slightly skewed x, maybe. So what does this look like? First of all, just like with the t distributions, we're not going to write down the PDF or the CDF. They're too complicated to write down. We're not going to work with them directly. Also, like the t distributions, they depend on the sample size. That's why both the t distributions and the chi-square distributions are what we call sampling distributions. They intrinsically come from the process of random sampling. Now, we can picture the density curve of such a chi-square distribution, and they typically look something along the lines of this very skewed right distribution, where we won't say anything about the mean or the standard deviation, but what we can say is that the support values are all positive, and it depends on the degrees of freedom. So this might be something like degrees of freedom 3. And as you take larger degrees of freedom, they start to flatten out and actually start to approximate a normal distribution, just a very flat normal distribution. That'd be a chi-square with just degrees of freedom, maybe 20. And actually, that curve isn't so great. It looks more like this. So it flattens out. You can't take any values lower than 0. And these come from sample variances. So the way that we want to think about this is sample variances are more likely to be lower than higher in magnitude. Remember that sample variances are always positive. So this makes sense that we aren't allowed to get any negative values. And when we pick off sample variances at random, they tend to be clustered around this hump rather than being up near the right tail. So as an example, we'll work with an application from accounting. So certain businesses, businesses all file their taxes with the Internal Revenue Service, the IRS, and auditing processes can be automatic or instigated by discrepancies that are noticed by employees there. So there are some errors that can be so large, and slightly overcounting withholdings for employee income or undervalued property holding, that they start to raise suspicion about the financial accounting. So suppose for a certain kind of business that we have this random variable x, which represents the number of accounting errors. In a tax filing, and we suppose that it's normally distributed for the sake of illustration. We'll just say that the mean of that distribution is 4.5, and the standard deviation, so the population standard deviation, is 0.86. So two things. One, well, actually, before we get to that point, I need to say that suppose we take a random sample. So random samples of size 50 for an auditing process, and determine sample variances S squared of the accounting errors, right? So then, what is the sampling distribution of the sample variance, S squared? And two, what is the probability that we find a sample variance at random no greater than 0.677. So remember, this is our population standard deviation. So our population standard deviation is the parameter we're trying to estimate. And S, the sample standard deviation, is an estimate of that. So, first of all, one, what can we say about S squared? We know, based on the scenario, because the underlying distribution is normal, then W, which is n minus 1, because n is 50, we have 49, times S squared divided by the population standard deviation squared, which is 0.7396, has a chi-square distribution with degrees of freedom n minus 1, 49. And now we can answer questions about the sample variance by just modifying it slightly so that we are answering questions about the W random variable. So 2, what's the probability that S squared is no greater than 0.677? Well, that's equivalent to saying, through a not standardization process, but we're transforming it into this new variable that we can actually say things about, then the specific W value, right, the chi-square value, is 49 times 0.677 squared over 0.7396. And when we simplify that, that ends up being 44.85. So this whole question is equivalent to asking, what's the probability that the chi-square distribution spits out random outcomes no greater than 44.85? And so we get, using technology, because we can't do this by hand, we can either use chi-square CDF on a TI-84, or we can use a chi-square cumulative area table. The chi-square CDF function is on a TI-84, and a chi-square cumulative area table is also provided to you in the appendix, but you can also Google it if you want. And so we find that this is 0.3580. That's the probability that we find a lower sample variance than that. And if we want to visualize this, even though we don't have the tools to actually calculate the density curve, we can imagine that we have something that looks like this. Sorry, actually, that's not very good. Let's do that better. Gotta have a very sharp tail. That's better. And so what we're saying is that 44.85, let me make that a little bit better. Is defining the lower tail that is exactly equal to, in area, to 35.3580, or roughly 35.8%.